Readiness status is one of the required test functions for a scan tool. In this mode, all of the system monitors will be displayed along with corresponding messages indicating if the tests have been run. Keep in mind that readiness status does not indicate whether a given monitor has passed or failed, only if the PCM has executed the test. The messages used to indicate readiness status vary among scan tools. For monitors that have run, the scan tool should display COMPL or complete. The following scan tool messages are typical for monitors that have not yet run: penned or pending, or incomplete. If a particular monitor is not used on a vehicle, the scan tool may display not supported. Because the continuous monitors are run repeatedly throughout the trip, the scan tool will always display them as being ready. However, non-continuous monitors may not be set to ready if the driver doesn't operate the vehicle in a way that satisfies all of the necessary enabled criteria. Additionally, the scan tool will display the non-continuous monitors as not having run if the battery or PCM is disconnected, or if the DTCs have been cleared using the scan tool. Monitor readiness status is an indication of whether the PCM has tested all of the vehicle's emission controls. In states using OBD2 that's inspection maintenance test programs, one or more monitors displayed as not ready may cause the vehicle to be rejected for the test. A misfire can be broadly defined as being either a partial misfire or a total misfire. A total misfire is a complete lack of combustion. Under this condition, the air-fuel mixture leaves the cylinder unchanged. Consequently, the cylinder makes no contribution to engine power. In the case of a partial misfire, combustion is incomplete. This causes the cylinder to generate only a portion of its potential energy. Whether partial or total, misfires not only result in reduced performance and increased emissions, but pose a serious threat to the catalytic converter as well. This is due to the excessive heat produced when the unburned mixture from a misfiring cylinder ignites inside the converter. Converter temperature is further amplified due to the response of the closed-loop system. During a misfire, unused oxygen is released into the exhaust. This causes a reduction in O2 sensor voltage, which the PCM interprets as a lean condition. As a result, the PCM increases injector pulse width, causing additional fuel to enter the converter. Misfires fall into one of 5 categories, including mechanical, electrical, lean, rich, and density. Mechanical misfire. Efficient combustion requires cylinders to be properly filled, sealed, and scavenged. Any breakdown in this series of events will cause the affected cylinder to misfire. For example, if the intake valve fails to open due to a worn cam lobe, the cylinder will not receive the volume of mixture required for proper combustion. If the cylinder is leaking because of a blown head gasket, for instance, the mixture will not be adequately squeezed during the compression stroke. Under this condition, the piston will be unable to compress the mixture sufficiently to produce the required increase in cylinder pressure prior to ignition. Finally, unless combustion byproducts are quickly discharged from the cylinder during the exhaust stroke, the incoming air-fuel mixture will become displaced by lingering gases incapable of supporting normal combustion. Consequently, an inactive exhaust valve is another potential cause of a mechanical misfire. Electrical misfire. Unlike a diesel engine, cylinder compression in a fuel-injected engine is not sufficient to ignite the mixture under normal conditions. Consequently, gas engines rely on a high-voltage spark to initiate the combustion process. An electrical misfire occurs when one or more spark plugs fail to fire. Electrical misfires are most common on engines that use spark plug wires, since the secondary cables are typically the weak link in the ignition system. Lean, a condition caused by unmetered air entering the combustion chamber, causing the air-fuel mixture to have significantly more air than desired when spark is initiated. The mixture has no conductivity, thus causing a lean misfire. Unmetered air is air that is not accounted or measured for by the MAF sensor. Typical areas for unmetered air to enter are leaking intake manifold gaskets, leaking injector O-rings, cracked or loose vacuum lines, and cracked or leaking exhaust manifolds or system pipes in front of the pre-catalyst heated oxygen sensor. Rich, a condition caused by too much fuel entering the combustion chamber, causing the air-fuel mixture to have significantly more fuel than desired. When spark is initiated, the mixture is too dense and the spark cannot promote a flame, thus causing a rich misfire. Some examples of typical causes for rich fuel conditions are leaking injectors, stuck closed fuel regulator, engine oil for a leaking head gasket or intake gasket, ECT circuit or sensor failure. Density, a condition caused by too much recirculation of exhaust gases, not the intake airstream. This condition is typical on vehicles with EGR valves. Hyundai uses CVVT to fulfill OBD EGR requirements. Flooding the intake airstream with recirculated exhaust gases cause the combustion chamber temperature to lose combustion heat, which renders the AF mixture inactive because the density of the chamber has been lowered to a point where the flash or ignition for motion is not possible. Examples of typical density conditions are stuck open EGR valve in Melco systems. As for CVVT systems, monitoring the EGR flow on the GDS should provide data to diagnose potential CVVT processing concerns. There are three types of misfires. Type A is the most serious condition, since it's based on a misfire that can raise converter temperature beyond 1800 degrees Fahrenheit. With the Type A misfire, the PCM will flash the MIL once per second and store a hard DTC and freeze frame data on the first trip. Once the vehicle begins operating in a range where the misfire no longer puts the converter at risk, the MIL will stop flashing and remain on steady. Be aware that the EPA does not require the MIL to flash if the system has an alternate catalyst protection method. For example, on some vehicles, the PCM will disable the injector of the misfiring cylinder to reduce the risk of converter damage. That's why in some cases the MIL may not flash when a Type A misfire occurs, but rather remain on steady. Type A misfires are typically caused by problems in the ignition system, such as an open or shorted plug wire or a defective coil. Type B misfire is a condition that can cause emissions to exceed 1.5 times the FTP, or Federal Test Procedure, standard, while the severity of a Type C misfire is based on emissions levels exceeding California IM standards. The first occurrence of either a B or C type misfire will result in a pending DTC with accompanying freeze frame data. If the misfire occurs on the next consecutive trip, the PCM will illuminate the MIL and store a hard DTC. Type B and C misfires will also result in an illuminated MIL and hard DTC if they occur on two non-consecutive trips within an 80-day trip window under similar operating conditions. Type B and C misfires are generally the result of a fuel control or EGR problem. There are 13 generic DTCs assigned to misfire detection. Depending on the application, the PCM will either store a DTC for each misfiring cylinder, up to 12 cylinders, P0301 through P0312, or simply store a P0300. This code indicates that a random or multiple cylinder misfire has been detected, which typically indicates that the misfire is not specific to a cylinder, but shared or common ignition components to cylinders.